Hello everyone. So this is our last video on chemical equilibrium, and we are continuing to look at these variables that affect the equilibrium in, say, a water sample. So we covered temperature, pressure, and side reactions in the previous video. What I would like to cover in this video is how ionic strength affects the equilibrium. So I'll define ionic strength, and then I'll also walk you through some calculations to help you understand how ionic strength affects the equilibrium and why it's important. So the book definition of ionic strength is the total effective concentration of ions in solution. So what ionic strength is, it's a measure of the ions and charge, their concentration and charge in solution. So it takes all the charges of all the ions, no matter if they're positive or negative, and allows us to give that quantity a number. And so what we're interested in is the spectator ions. We're not talking about the ions that are participating in some sort of equilibrium calculation. We're interested in all the other stuff. For example, if we're interested in a reaction in the ocean, we're interested in all the salt. So we're going to calculate the ionic strength of all the salt in the seawater, and that's going to help us understand our small little reaction. And so the way that we calculate ionic strength is with this template of an equation here. And we'll do an example below and make it a lot easier than what it looks. And so essentially all we're doing is we're adding up all the concentrations times the charges. The charges are squared of all the ions. We add them up, sum them up, and then once we've done that, we divide by 2 or times by 1/2. So these are the concentrations. Z is the charge of the species, and the charges again are squared. So we add all those up, we divide by 2. So I will, on your midterm exam, ask you to calculate the ionic strength of a solution. So let's look at this example. So what's the ionic strength of a 0.01 molar sodium sulfate solution? So the first thing we need to do is we need to break it up into ions. So here, well, I recognize from the formula that we have 2 sodiums. And so the molar concentration of sodium plus isn't going to be 0.01, it's going to be 0.02 molar. Because for every sodium sulfate, there's 2 sodiums. And we need to know at this point that sodium has a +1 charge, or look it up. And perhaps I will put on Canvas some resources to review the charges of ions and even their names and symbols. Sulfate has a 2- charge. And so when this salt turns into its ions, there's 1 sulfate for every sodium sulfate, so the concentration stays the same. So now we know the concentrations of the ions, we know the charges on the ions. We now put it into the equation. Here's my sodium ion. Here's my sulfate ion. I take those numbers, divide by 2. So I get an ionic strength for this solution of 0.03 molar. So now we're going to take it a step further. So that's the first step, is calculating the ionic strength. The second step is applying it to the equilibrium. And so let's take this step by step. What we can do with the ionic strength is we can look in tables and find activity coefficients. So these values are found in tables. Every ion has one of these coefficients, and we can start using these coefficients to show how the ionic strength is going to affect the equilibrium. And so what we're going to do now is kind of change our definition of equilibrium. We're actually going to use the proper definition of equilibrium. And so rather than in an equilibrium expression, we use concentrations. The actual definition uses what we call activity. Activity is the concentration that's actually measured, not what is in theory, but what's actually measured. And so that's where we're going here. The ionic strength affects what we measure. All those salts affect what we measure. And so we need to relate what we measure to the theoretical calculation, or excuse me, the theoretical concentration. And that's what we have here. The activity of a chemical species, the concentration that we actually measure, is equal to the concentration, as we know it, times the activity coefficient. So you can think of the activity coefficient as something that relates the concentration with the activity, what we actually measure and what we should be measuring. So when we first started to talk about chemical equilibrium, we started with this generic equation. A plus B goes to C plus D. And when we did that, we came up with an equilibrium expression, which is the products over the reactants equal an equilibrium constant. And so we have the concentrations of C and D over A and B, and we have put the coefficients here as exponents on the concentrations. But the actual definition for equilibrium doesn't use concentrations, it uses activities. The effective concentration, the concentration that you actually measure in solution, because there's a lot of other things going on in the solution. So at this point, we're going to get rid of our old equilibrium expression, which we can still use if we're calculating concentrations in pure water, which that's what we do in most textbooks. But since we're going to study environmental systems with all different types of things in them, we want to at least think about the true definition and how we can use that in some circumstances. And again, I think the ocean is a good example of where this relationship is more applicable than the ideal situation. So we'll get rid of this. And so now with our new equilibrium expression, we take the relationship that we had on the previous slide, which said that the activity is equal to the concentration times the activity coefficient. We do that for each of these activities. And so now we get this relationship. This is equal to the equilibrium constant. So let's do an example and see what we're actually going to do and how we'll kind of move things around. So let's look at the following. So let's say we have a certain reaction. This is the solubility of silver sulfate, and it has some KSP value. So some constant that helps us determine how much of the salt actually dissolves. Well, we can write the equilibrium expression in terms of activities, and then we can add the activity coefficients. Remember, these activity coefficients are just something we get out of tables, so they'll easily be filled later. And so what we'll do, we're still interested in calculating these concentrations. So what happens is we then end up moving the activity coefficients to the other side of the equation and combine them with the equilibrium constant. Remember, all these variables, these activity coefficients and K, they're all constant. So now we're just going to wrap them up together and we make a new constant. This constant, which I'm calling KSP prime, this K prime, this now has incorporated the environmental conditions that we're trying to measure this equilibrium in. So in this way, I now have a new K value that takes into account the ionic strength. So now, at this point, KSP prime equals the concentrations under these new conditions, taking into account the ionic strength, and now I can do the calculation as I did in the past. So that's it. That's all we have to do. So we just need to include the activity coefficients in our equilibrium. Once we've done that, we can move them all to one side with the K. We find a new constant, and then everything's back to normal. So one thing that we'll learn is that all these gammas are fractions. They're less than 1. So you can imagine what's going to happen here if all these values down in the denominator are less than 1. That means that when I convert KSP to KSP prime, that K value is always going to be larger. It's always going to be larger because of these, at least written for a reaction such as this, it's going to be larger because all the gammas are on the bottom. And what that means, if K is larger, that means that due to ionic strength, the larger K is going to shift the reaction to the right, meaning we're going to have a salt that's now more soluble. Silver sulfate is more soluble as ionic strength increases. So we'll get more into that, but I just wanted to kind of let you know ahead of time how we need to think about this. So here, so what we'll find is that K prime is equal, or I should say moves towards K as I approaches 0. So what that's saying is as we get to pure water, as we move to less and less ionic strength, and once we get to pure water, K prime is equal to K. And again, that's what you cover in all your textbooks. Typically, when you do a calculation, is you're just assuming pure water. And also, as you get to pure water, the coefficients that are present, they all approach 1. Because as you get less and less ionic strength, they get closer and closer to 1. Also, what we'll see in these tables is that increasing charge, if you go from +1 to +2 to +3, their activity coefficients are way smaller. They have a much bigger effect on the ionic strength, changing the ionic strength and changing the effects of the equilibrium. And this is due to a higher masking effect, which we'll talk about next. So here's an example of a table that looks at ionic strength. So these numbers up here are different ionic strengths. And then from there, we just need to find our ions. So we were looking at silver. Do we see silver here? There's silver. And let's say we're at 0.01. So there is the value of the activity coefficient, gamma. And then we have sulfate here. Let's say we're at an ionic strength of 0.01 again. We have to line up straight, and we get a value of 0.661. But notice how as we go to lower and lower ionic strength, the values get closer and closer to 1. Also look and see as we get to higher and higher charges, like +4, -4, things like that, and we get at higher and higher concentrations, the activity coefficients get very small, and they're going to have a larger effect on K when we include them in the equilibrium expression. So let's talk about this masking effect. Why does ionic strength affect the equilibrium? Why does it make a, say, solid more soluble? Well, this will be my first take on this. We'll do an example next to kind of help us understand. But what we can say is that these ions create this masking effect that makes it more difficult for ions that are actually participating in the equilibrium. It makes them harder to actually come back together. Because you can imagine if you had this silver sulfate, you had silver ion and sulfate ion floating in solution, and what they want to do is find each other, bond, make the solid, then the solid will dissociate again and turn back into ions. And that's the equilibrium that's being set up. The ions come together, form the solid dissociates into ions, and that's in balance where the forward and the reverse reaction are the same. We have this equilibrium set up. But what happens when you introduce ions, just other ions, spectator ions, sodium, chloride, things like that, is when the species are in the ion stage, in the silver plus and the sulfate 2-, they have a hard time finding each other given that there's all these other charges around. In that way, it shifts the reaction to the right. It shifts it towards the ions. So an example is, say, this reaction in the ocean. This is a very important reaction in the ocean. It's very important with ocean acidification, because this dissociation, this is an acid dissociation. So we have bicarbonate here, and at equilibrium, it produces some protons, some acid, and some carbonate. And this reaction is, again, in equilibrium. It goes both ways. However, in sodium chloride solution, or say in the ocean, the ionic strength in the ocean is 0.7. It's very, very salty, lots of ions in solution. What we'll find is that this reaction shifts to the right. And again, this is my second attempt to convince you that this happens. Because of all the salt in the ocean, the ions, these ions, have a more difficult time finding each other and having the same electrostatic attraction for each other, because there's all these other charges around. They have a harder time coming together to form, let me do a different color here. They have a hard time coming together and forming the bicarbonate. What that does then is shifts the equilibrium this way, because this still is not affected. This species will still dissociate. It's not affected, its dissociation is not affected by the ions, but the association, these two ions coming together and having the reaction go to the left, that's the issue. And so because of that, because of the ionic strength, we get a lot more acid in the ocean compared to a situation where we're in fresh water. And so here's our equilibrium expression. And again, we'll substitute these activities for the concentration times the activity coefficient. Did that for all three. This is a Ka2. We'll talk about that in chapter 3. This reaction is the second dissociation of carbonic acid. You guys will get familiar with that. But we can calculate, if we had the numbers, we would calculate Ka2 prime. So this is, you could say that this is the second dissociation constant of carbonic acid in the ocean. So this constant here we would use for any calculations we do in the ocean, which has been corrected for the ionic strength. And so again, we would look up all these numbers, look up the K values, look up the gammas. Now we can actually do calculations on species in the ocean and calculate, say, the pH of the ocean. And we'll do that in chapter 3. So let's do one example. And so what we're going to do is we are going to calculate the molar solubility of barium sulfate in 0.1 molar sodium chloride. So we know that these salts are going to affect the solubility of barium sulfate. And so we have this solid, this salt in solution sitting at the bottom, but it's in equilibrium with its ions. We have very little barium, very little sulfate. We're not going to use those numbers or those values to calculate the ionic strength. The ionic strength is going to be calculated from all this salt in solution. So if we think back, the first thing we need to do is calculate the ionic strength. Once we have the ionic strength, we can look in the tables and we can look up the activity coefficients for barium and for sulfate. That's the plan. And from there, we'll be able to calculate a new equilibrium constant and then find the solubility. So that is the plan. So first, before we do anything, let's calculate the ionic strength of a 0.1 molar sodium chloride solution. So I have our equation here, and I put in our ions so that you can follow. I put in the concentration. It's all both 0.1 because it's all 1 to 1, right? For every 0.1 molar sodium chloride, I have 0.1 molar sodium ion, 0.1 molar chloride ion. The charge on chloride is -1, charge on sodium is +1. I do the math. The ionic strength of a 0.1 molar sodium chloride solution is 0.1 molar. So I look and I find ionic strength of 0.1 molar. And I see barium here. And I see sulfate here. And so here are my two activity coefficients that I'll use in my equilibrium. So I have those. And so now we can finish the calculation. So now we're going to do this problem similar to what we've done in the past. The first thing is I am trying to figure out the solubility of barium sulfate. So I need to write an equation expressing the solubility of that solid. And I've done that. I have been given the equilibrium constant of 2.0 times 10 to the -10. That is equal to the activity of barium times the activity of sulfate. I can rewrite that in terms of concentrations, and I'm going to include the activity coefficients. This is our third time we've done that. And so with that, I move the activity coefficients to the other side, and I create one brand new equilibrium constant, K prime, that incorporates the equilibrium under these new conditions at 0.1 molar ionic strength. And so here it is. I do want to say that in the notes that I have online at PDF, I miswrote 0.36 there. It's actually 0.35 in the tables. So these numbers are correct. So if you use those notes, you might want to make that correction. K prime is no longer 2.0 times 10 to the -10. It's 1.5 times 10 to the -9. It's actually about a magnitude larger now because of the salts. That's going to affect the solubility. And so that new K value equals barium concentration times the sulfate concentration. I'm going to let the solubility equal X. I can see that for every one of these salts, I'm going to make one of these and one of these. So whatever concentration of barium I have in solution, I'm also going to have that same concentration of sulfate. So I'm going to let them both equal X. I then solve for X, and I get 3.8 times 10 to the -5 molar. That is the solubility in 0.1 molar sodium chloride. Now, if I was to use the original K values, so essentially calculating the solubility of barium sulfate in pure water, what I find is, again, it's much less soluble than when we have the salts. That's due to the masking effect. That's due to the fact that the ions have a hard time finding each other and binding together to move the reaction to the left. But the reaction going towards the right is still at the same rate. So in looking at this video, I would say there's three things I would like you to know. I would like you to be able to calculate the ionic strength of a solution. So that will most likely show up on a midterm. The second thing, I would like you to be able to explain to me how that affects the equilibrium. So you can explain it in terms of the masking effect. You could explain it in terms of the equilibrium and the forward and reverse rate of the products and reactants, but you need to be able to explain to me how the ionic strength affects the equilibrium. And thirdly, at least on a worksheet, I would like you to be able to do a calculation like this last sample problem. So I think that would be a good exercise for you. Again, this is a very important topic in environmental chemistry because we do not work very often in pure water. We're working in natural systems where there is a lot of different ions and chemical species in solution, and so we need to take into account things like the ionic strength.